We are asked to find all zeros, real or complex, for the polynomial p of x is equal to x cubed minus x squared minus x minus 15. Now, the rational zero theorem is going to help us because in a problem like this, we do have to start off by guessing. And it seems like an odd thing to start a math problem by guessing, but we really don't have much other choice here. Now, the good news is the rational zero theorem will help us determine what we need to use for guesses. In this case, our leading coefficient is a 1. So according to the rational zero theorem, if your leading coefficient is a 1, you don't really have to mess with any fractions. We're going to do everything with integers. Now, our possible rational zeros are factors of our constant term, q. So in this problem, our constant term is negative 15. And the factors of negative 15 are plus or minus 1, 3, 5, and 15. So we're going to start off by guessing positive 1. Now, you can check to see if a constant is a zero of the polynomial by simply plugging the number in and then adding it up. If you get 0, then yes, the number is a 0. If you don't, well, then it's not. In this case, though, since the second step of our problem is going to be perform a synthetic division anyway, it is easier for us to go ahead and check for zeros by using synthetic division with the number that we want to check on. And if we get a remainder of 0, then the answer is yes, that is a 0. If we don't, then the number is not. For instance, if we use synthetic division for positive 1, and I write down the coefficients for p, which are positive 1, negative 1, negative 1, and negative 15, and perform my synthetic division. I bring my 1 down, and we multiply. Negative 1 and positive 1 is actually 0. 0 times 1 is 0. Negative 1 gives me negative 1. And I end up with negative 16 as my remainder. Well, that's not a 0, so positive 1's no good. We have to try something else. Now, we could guess all the positives, 1, 3, 5, 15, or we could go back and forth, positive 1, negative 1, positive 3, negative 3. I've found in my experience that it's better to go back and forth between the positives and the negatives. So my next guess is going to be negative 1. Again, I write down my coefficients 1, negative 1, negative 1, and negative 15. And I get 1. 1 times negative 1 is negative 1. Gives me negative 2 times negative 1 is positive 2. Positive 1 times negative 1 is negative 1. And again, I am getting a negative 16. So once again, the answer is no, this will not be a 0 for my polynomial. Now, once again, I'm only trying factors of 15. So if you're thinking my next guess might be 2 or negative 2, you would be wrong because 2 is not a factor of 15. We're going to go to positive 3. So if I try synthetic division with 3, 1, negative 1, negative 1, negative 15. I bring my 1 down and multiply. Negative 1 and 3 gives me 2. Times 3 is 6. Negative 1 and positive 6 is positive 5. Times 3 is positive 15. And negative 15 and positive 15 add up to 0. My remainder is 0. So that means that 3 is, in fact, a 0 of the polynomial. The remainder theorem says if I plug 3 back in everywhere I see an x and add them up, I would get 0. So this is one of my answers. Now the problem is, for a third degree polynomial, I know that I'm going to eventually need 3 answers. So what I'm going to do is I'm going to look at the division problem I've just completed. Our factor theorem says that if I can divide by 3, then my polynomial will be equal to x minus 3 times the quotient of my division problem. In this case, my quotient is x squared plus 2x plus 5. Remember, when you're looking at the synthetic division, the last term is your constant term, the second number is your x to the first term, and your third number is your x to the second term. So my polynomial is x squared plus 2x plus 5. I have partially factored my problem. Now, I continue to factor if I can. However, notice in this problem we do have sort of a roadblock. My leading coefficient is 1. It's a basic quadratic. But there are no two numbers that I can multiply together to give me 5 that will add up to 2. That means I cannot factor this. But the good news is this is a quadratic expression, so I can solve it using any method for solving quadratic equations that I happen to know. So what we're going to do, we are again setting this function equal to 0 and solving it, so I can set each factor equal to 0 and solve each of those equations independently. Well, my first equation gives me x equal 3, which we already knew that was one of my answers anyway. Now I'm going to solve this quadratic equation. I've already determined I can't factor it. I could use the quadratic formula, but I'm going to do something a little different here. I noticed that this problem would be pretty easy to do with the complete the square method. Now, if you don't like complete the square, feel free to use the quadratic formula to solve this, but let me show you how easy this could be in this particular problem. I'm going to bring down my x squared and my 2x. I'm going to move my 5 to the opposite side of the equation and make it a minus 5. So I'm going to give myself a little more room there. Minus 5. Then I'm going to take half of 2, 1/2 times 2, and square that result. Well, that would be 1 squared, and that's equal to 1. So I'm going to add 1 to the left side of the equation, and also, to keep my equation balanced, I'm going to add 1 to the right side of the equation. So what does that do for me? Well, I can now factor the left side to x plus 1 squared, right? X plus 2, x plus 1 is x plus 1 times x plus 1, or x plus 1 squared. The right side would be negative 4. Now I can use my square root principle and say that x plus 1 is equal to plus or minus the square root of negative 4. Now, you may be thinking, I can't take the square root of negative 4, but remember the question does ask us for all zeros, real or complex. All the square root of a negative means is our answer will be a complex number. The square root of negative 4 would be 2i. So I get x plus 1 is equal to plus or minus 2i, and finishing, I get x is equal to negative 1 plus or minus 2i by subtracting 1 from both sides. Again, remember I said if we have a third degree polynomial, I should have 3 solutions, and I do. Positive 3 is one of my solutions, negative 1 plus 2i is my second solution, and negative 1 minus 2i is my third solution.